Very good. Great success. But how? Alright class, listen up. Today, we're talking about solid rocket boosters. Our great and powerful vehicle, Obama Prism, uses a weird little solid rocket booster to propel itself upwards. But what is a solid rocket booster? Well, a solid rocket booster is a booster that uses a solid fuel. I know. I wouldn't have figured that one out either. The solid fuel is made up of an oxidizing agent and a fuel. Think of it like a high-powered explosive that explodes gently. When it's lit, the rocket burns this fuel and creates a very hot gas. Now Kevin, please remind the class about Newton's third law. Every action... Okay Kevin, I'm gonna need you to be quiet. I did not ask. Anyway, Newton at one point was like, every action has an equal and opposite reaction. Basically, push on something, and the thing pushes back. This principle is how literally everything moves. Your car pushes the ground, which pushes back on the car. An airplane pushes the air pushes the plane. Simple. So, when the hot gas shoots out one end, what happens to the rocket? It goes forward. Shut up, Kevin! It goes forward in the opposite direction of the gas, thus creating thrust. So, when we smash that spacebar, the rocket goes up. Incredible. Class dismissed. But why is Jeb dead? Okay class, sit down and buckle your fuckles. In this lesson, we're doing aerodynamic stability, and what even is space anyway? So what actually happened? Well, if we rewind the video, you'll notice a minute and difficult to catch detail that led to Jeb's death. If you look really close, you can see he smashes into the water at several times the speed of sound. Interesting. But why? Passive aerodynamic stability. I want you to imagine a dart flying through the air. The dart can only point in one direction, forward. If you try throwing a dart backwards, it'll just go and point forwards again. This is because a dart has wings at the back and its mass at the front. The dart is passively stable when flying forwards and unstable when flying backwards. Similar situation with the late Obama Prism 2. The mass is concentrated towards the front of the vessel where the capsule is, and the little wings act to keep it stable in the forward direction. Unlucky for us, this direction also happens to make the capsule very aerodynamic, i.e. it doesn't slow down. As we re-entered the atmosphere, the little reaction wheels in the capsule kept it pointing backwards, but once the air got thicker, it pushed on the wings and forced the ship into a nosedive. Once in this position, the craft acts very much like a dart and doesn't slow down enough to open the parachute, ending with Jeb smacking straight into the water at twice the speed of sound. Rest in peace, Jeb. Before Jeb met with the ocean at Mach 2, he managed to fly completely out of the atmosphere, topping out at over 100 kilometers. In KSP, the atmosphere ends at exactly 70 kilometers. You can easily tell when you're there, because the music goes like... On Earth it's a little less clear-cut, because there are technically air molecules all the way up past 400 kilometers, but the generally agreed upon altitude that space begins is 100 kilometers, known as the Kármán line. So why is this important? Well, we'd like to get to orbit eventually, which means we'll need to be traveling really fast in one direction. Air doesn't like it when you go through it really fast, so we avoid the air altogether by going up nice and high. Air doesn't reach higher up because Kerbin's gravity pulls it all down to the surface. Also, Kevin, please just be quiet next time. The class is trying to learn. I didn't say anything, bro. Shut up! Just shut up. Class dismissed. But we also didn't make it to orbit. Why? Okay class, keep those fuckles buckled. Today, we're learning basic orbital mechanics. Among some other things. First off, why do we shoot parts off the rocket? Why not instead just make a long noodly rocket that has all the fuel in a single tank? I'll tell you why. Mass. When these tanks are empty, they still contribute mass to the vessel. Hey, psst, hey, Kevin. What equation is Newton most famous for? That's right, force equals mass times acceleration. Oh yeah. If we do some high-level algebra, we can rearrange this and get acceleration is force divided by mass. When the mass is lower, the acceleration is higher. Thus, eliminating excess mass makes you go faster. Very nice. After ditching our first 3 solid rocket booster stages, we get this special engine on our last stage. This is a liquid-fueled engine. Instead of burning a solid propellant, it mixes fuel and oxidizer inside the engine to create the hot gas. Liquid engines are much more efficient than solid boosters and can be throttled and even turned off. Oh yeah, I forgot to mention, solid boosters can't be turned off. Once you start them, they go. And go. And go. Liquid-fueled engines are pretty cool, but they come with a price. Literally. Just the engine, without the fuel on this rocket, costs as much as all 3 of the solid rocket boosters combined. So solid boosters make economical sense for sections that don't need the greatest efficiency. Now of course, the elephant in the room. No, not that elephant. He's purely ornamental. Our failure to reach orbit. Gravity. Gravity pulls at all objects with mass. Our spacecraft has mass, thus it is subject to gravity. Wow. Gravity pulls with a force depending on how far away from the body you are. If the mass and distance are kept constant, the force is also kept constant. Meaning, if you can generate enough force in the opposite direction, you can fly. Now of course, there are many ways to... Dude, really? You're just gonna fucking stand there? Come on dude, get out of here, bro. As I was saying, there are many ways to generate force. Wings, brakes, engines, parachutes, magnets, electric fields, mass, just straight up pushing on shit. You get the idea. But today we want to look at centripetal and centrifugal forces. Both of these forces exist when something is rotating. Well, technically centrifugal force doesn't actually exist, but I'll leave that as an exercise for you to explain. Answer in the comments. Do it now. The common example is a ball on the end of a string. Centripetal force is the force that the string exerts on the ball, while centrifugal force is the force that the ball experiences in the opposite direction. Now how does this relate to Obama Prism 3? Well, as you probably have experienced, the faster you spin a ball in a string, the harder it pulls away from you. This means that our imaginary centrifugal force is increasing. Once it goes past the force generated by gravity, we achieve orbit. But we didn't do that, so on to... Wow, would you look at that? It's hot. Very hot in fact. So hot that it's learning time. Friction. Friction is all around us. Have you ever walked? Friction. Moved in a car and then stopped moving in a car? Friction. Rub 2 metal plates together so hard they form a robust friction weld? Friction. That last one is important. It demonstrates how friction generates lots of heat. So tell me, Kevin, why is there a giant plasma flare around casting couch? Friction? Yes. In case you didn't realize, our craft is moving really fast. Over 2,000 meters per second in fact, which translates to roughly 32,927 Big Macs stacked vertically every single second. Pretty quick. As you can imagine, this means we have lots of kinetic energy. If you've ever ridden a bike with disc brakes, you'd know that using the brakes converts your speed into heat within the brakes. Ah, fuck! Exact same principle here, just with much more speed. The amount of kinetic energy something has is related to the square of the velocity. This sounds kinda complicated, but it just means that when you double your speed, you quadruple your energy. So casting couch has a huge amount of energy. Hence, when it slows down, giant plasma flare. Nice. And there we have it. We went to the moon, and didn't die. But how? Nope, that's enough. I would do the next lesson, but it looks like we're out of time. And more importantly, I'm getting a little sick of it. So it looks like we'll have to wait for next episode. That's right, there will be another episode. But you might need to wait. In the meantime, subscribe to my channel. Now. Almost got to orbit. Actually got to orbit. Told Kevin off for being a terrible student. Yeah, you heard me. Very nice. We're left with precisely 6,262 meters per second of delta V. Oi sir, what's delta V? Speed. Quite simple. It's how fast you're moving. For example, 4 meters per second. Or, for my American viewers, 2.77 Barrett M82A1s per second. Velocity. It represents speed, but with direction. 4 meters per second, to the right. In physics, and in maths, the capital delta from the Greek alphabet refers to a change in something. So, delta V would be a change in velocity. For example, we're travelling forwards in a straight line at 100 meters per second. If we point our craft forward, how fast would you expect we go after burning all of our fuel? 200... Well, since we have a... Kevin? Be quiet. Well, since we have 150 meters per second of delta V, we'd expect to be going around 250 meters per second. And sure enough, we do. If we face backwards and do the same experiment, we go 50 meters per second in the opposite direction. Nice. So why is this useful? Well, it basically measures how far our craft can go. Remember, our craft is being pulled by gravity. In order to escape its influence, we need to go fast. In order to go fast, we need to change our velocity, and thus, we need delta V. Poor Urk.
Oi, sir.
We then set time acceleration to 1 million times and quickly got to the transfer window.
Oi! Just wondering what a transfer window is?
Nah, that's it. I've had enough. Anyway, class, you may be wondering what a transfer window is.
Oh yeah, that's what I wanted to know.
Today, we're learning some more basic orbital mechanics. So, here I am, in orbit at 75 kilometers in altitude, only just above Kerbin's atmosphere. Here is Jim. Say hi, Jim. He's orbiting at 150 kilometers in altitude. Which one do you expect orbits Kerbin faster? If you said Jim, you're wrong, and you should feel bad. I orbit faster. But why? Well, firstly, if you cast your mind back to circle geometry, this circumference is smaller than this one, so it has less overall distance to travel. On top of this, my craft is experiencing stronger gravity because it's closer to Kerbin. Stronger gravity means we need more force in the opposite direction to cancel it out, which means we need to go faster. Hence, our speed is higher, and our distance is shorter, making each orbit much faster than Jim's. This demonstration also applies to planets. Kerbin is closer to the Sun than Duna, and thus orbits faster. Oh, what the fuck? Hold on, let me fix that. Ah, there we go. A nice round orbit created by our large amounts of fuel and delta V that we absolutely had on our rocket without question. No questions. So, after a long and tedious design... Okay, let me let him back in. Anyway. So basically, science times 5. Pretty pog if you ask me. Now, Mr. Kevin.
Oh yeah?
I'm going to issue you a challenge. If you can design the transfer craft and launcher for this base, I won't throw you into space ever again. Oh, and you have 4 seconds. Go. Okay, time's up.
Oh, yeah, I think I did pretty good.
Let's see what you got for us, Kevin. Oh my god. It's beautiful. The optimized engines, the fuel ducts leading into the center stage, the 300 kilograms off the mass limit, the slightly scuffed fairing.
It even has a watermark.
Okay, so, Kevin? It's bad. Anyway, we're gonna use this vehicle to take us to Duna.
Oi! Why'd you throw me out? You're using me craft.
Yeah, anyway. Let's get this guy up and into orbit. Thank you, Urk. Godspeed. Oh, wait, what the hell? Where'd he go? Kevin? Hey, Kevin, what are you doing? What the fuck? Where'd you get that from? Kevin, get back. Kevin, what the fuck? Where'd you get Kevin? I'm doing my own thing. Fuck you. Kevin! Where'd he go? What the hell? He'll come back, right? Right? Well, anyway, where were we? Wow, would you look at that? It's getting hot. Really, really hot. Must be all that friction, right? Yeah, that friction really generates a lot of heat on re-entry, doesn't it, guys? Yeah, friction! Definitely couldn't be any other mechanism other than friction! Oh. Hello? Yeah, who is this? Wait, what about the YouTube comments? Oh, it's not friction? Huh. No, I didn't get it wrong in the last video. You see, there's this guy in my class, and he's called Kevin. Hello again? It's me, Vsauce Derek. I'm here to talk to you about compression. No, not video compression. Air compression. Air compression is actually what causes the heating on re-entry. But how? Well, first off, what is air made of? Pretty simple. It's made of molecules. A whole lot of molecules. Now, what is temperature? Also pretty simple. It's how much a given molecule or atom is vibing. More vibes equals more kinetic energy, which equals higher temperature. Fairly simple. So as you can imagine, if you squish a bunch of air molecules together, they're going to bump into each other quite a lot. Bumping into each other equals more vibes, which equals higher temperature. Now normally moving around in the air doesn't burn you to a crisp because the air molecules can get out of the way. However, say we're traveling at a modest 3 kilometers per second. The air molecules now don't have any time to get out of the way and are compressed into a superheated plasma. Pretty cool. Actually no, pretty hot. Which is why we have this heat shield. Anyway, we don't burn up in the atmosphere, deploy the chutes, jettison the heat shield, deploy the legs, and touch down on the surface of heat. Very good. Now I know I said I'd do an ELU base this episode, but I can't be asked. Once again, you'll have to wait for episode 3. I'll tell you when the next one comes out, but only if you subscribe. This is not optional. Oh, and also follow my Twitter to gain deep insights into the human experience. This is also not optional. And while you're at it, like the video. Come on now. But let's back up for a minute. Why build a base on Minmus? Hello class, it's me, Frog Guy. In this lesson, we're going to learn about drag. Aerodynamic drag. Drag is a force that acts in the opposite direction that you're moving. If I move to the right, then I'll experience a force to the left. It slows stuff down. Not what we want for high-speed rocket flight. Or is it? Yeah, most of the time. But parachutes are very useful because they can create huge amounts of drag when you want them to, slowing a speedy craft down to not so speedy speeds. But, most of the time, drag is bad. So how do we get rid of it? Well, if we can find a way to lower these guys on the right, it'll result in this guy on the left also being lowered. Maths. Now let's say, hypothetically, I want to have no drag whatsoever. Since all the terms on the right are multiplied together, and we know that anything times 0 is 0, if any one of these numbers here is 0, then the whole thing is also 0. These guys on the right here can't really be 0. Area would mean our craft is a one-dimensional line, the drag coefficient can never really be 0, and if you made velocity 0, well, yeah. Last we could change would be fluid density. Now this can actually be 0. Now I wonder, where is fluid density 0? Kevin. Someone. Please tell me. Really? No one? Guys, come on, it's Minmus, you fucking idiots! I've had enough. God, why would you just pay attention to life? Yeah, Minmus. There's no atmosphere, meaning drag is 0. Good spot for a base, don't you think? Yes. But first, what is antimatter? Hello again, class. Welcome back. Particle physics. Sounds complicated, but it's really not that bad. Firstly, we begin with water. If you were to zoom in really close to water, you wouldn't see anything. But if you could see something, you'd see water molecules. Lots of water molecules. Let's pick one of these molecules and look at it even closer. At this scale, you can see that water is made of 2 hydrogen atoms and 1 oxygen atom, H2O. Let's ignore the oxygen for the time being and zoom into one of the hydrogen atoms. At this scale, we see that the hydrogen atom itself is made of 1 proton and 1 electron. Protons have mass and a positive charge, and electrons have almost no mass and a negative charge. Protons and electrons, and also neutrons which have no charge, make up matter. If we have a close look at oxygen, we see that it itself is made of 8 protons, 8 neutrons, and 8 electrons. So where does antimatter come in? Well, it's basically the opposite of regular matter. Antiprotons have negative charge, and anti-electrons, which are actually called positrons, have a positive charge. This means that antiparticles and regular particles are attracted to each other. So, what happens when they touch? Annihilation. All their mass gets converted to energy by Einstein's famous equation E equals mc squared. E being energy, m being mass, and c being the speed of light, which is squared. C squared happens to be this number, 9 with 16 zeros on the end. So if you had 1 kilogram of antimatter and mixed it with 1 kilogram of regular matter, you'd have this number of joules. A lot of joules. Or 21 megatons of TNT in 1 kilo. Pretty good stuff. Which means our lovely 1 ton of antimatter is the equivalent of 21 gigatons of TNT. Very big. But still 5,000 times less than the Dino Destroyer asteroid. Now that was a big boy. But before we launch, learn time. Let's rewind the tape a little bit. This big fusion engine for high efficiency. What do I mean by this? What makes a rocket engine efficient? First of all, let's look at a small example. These two rockets are both exactly 7 tons and have the same amount of fuel. The only difference between them is the engines they use. This one uses a conventional liquid fuel engine, and this one uses a nuclear engine. If we burn all the fuel in both rockets, which one will be going fastest at the end? The nuclear engine. Obviously, why else would we put a nuclear reactor in space? You dumb! So why is this? Conservation of momentum. You may remember back in episode 1 when I asked Kevin about Newton's third law. Every action has an equal and opposite reaction. The rocket engine expels hot gas backwards very fast, which imparts an equal and opposite force on the rocket, causing it to accelerate. If you throw the hot gas back even faster, then you get more force for the same amount of fuel. This is exactly what the nuclear engine is doing. It uses a nuclear reaction in its core to heat up a gas to incredible temperatures that are much higher than what normal chemical rockets can achieve. This hot gas expands more than regular hot gas, which gives it higher exhaust velocity, and thus higher efficiency. So what about our futuristic fusion rocket? How does that work? I don't know. But what I do know is that it uses a nuclear fusion reaction to release lots of energy and then shoots hydrogen through it to get its thrust. Efficiency is measured in specific impulse, which is measured in seconds. Higher seconds is better. But why seconds? 400 seconds would mean that a rocket engine with 100 kilograms of fuel would produce 100 kilograms of thrust for 400 seconds before it ran out of fuel. The best chemical rockets can do about 400 seconds of specific impulse. The nuclear rocket engine in stock KSP does 800 seconds, and the ion engine can do 4,000 seconds. This is still baby shit though. The fusion engine that we've been talking about can do 15,500 seconds in high thrust mode, and 27,000 seconds in the most efficient mode. But we can do even better. The best engines can do 100, even 200,000, with the very best able to do a ridiculous 2 million seconds of specific impulse. These engines are so powerful that they can realistically accelerate the craft to a significant fraction of the speed of light. Very nice.